Thank you. So now we will focus on the geometry of adelic curves. So this afternoon I will talk about the geometry of numbers for adelic curves. And in the last lecture I will explain the higher dimensional aspects. So we will fix an adelic curve which is supposed to be proper. Which is denoted by S. So I will give you a quick reminder on the definition. So this is just a field. K is a field. And this is a measure space. And the phi is a map from omega to a set of absolute values. Okay, which sends omega to an absolute value with index omega. And the condition is that for any A which is not 0 in K, so the function log of A with respect to omega is an integrable function with respect to omega. So, and moreover, if you integrate this function over omega with respect to this measure nu, we require that this is 0. So that is condition for the adelic curve to be proper. For simplicity, we assume that for any omega in omega infinity, which is the set of x in omega such that the absolute value indexed by x is Archimedean. So namely, if for any omega such that the corresponding absolute value is Archimedean, so this absolute value is the usual one. On K omega, which is either R or C. So K omega is the completion of K with respect to this absolute value. So of course, if you replace the usual absolute value by some power with exponent smaller than 1, you get another absolute value in the same class. But for simplicity, we assume that it is just the usual one. Okay. So as you can expect, we will treat objects like a vector space of finite rank over K equipped with a family of norms parametrized by the measure space. So let me give you the formal definition. So that E be a finite dimensional vector space. Over K. So we call norm family E. So any object like psi, which is a family of norms so where each norm is just a norm on ek omega. So this is just a family of norms. So for simplicity, we assume that for any omega which is non-Archimedean, so the corresponding norm is ultrametric. So this one verifies a strong triangle inequality. Yeah, I will erase now, yeah. Okay. Now you have several very usual construction. So for example, you can define a psi dual, which is a family of dual norms. So this is a normal family on the dual vector space of E. And this hypothesis of saying that for any omega non-Archimedean, this norm is ultrametric, implies that you have psi double dual is equal to psi. So if you take 2 times of the dual norm, you obtain the initial norm. So also you can define the determinant of psi, which is given by omega determinant omega in omega. So this is a normal family on determinant of E. So on the determinant space, you can consider determinant. So also, if you have a vector subspace, so this is a vector subspace. So you can consider a family F omega. So this is a restriction of the norm omega on Fk omega. So this is a vector subspace of Ek omega. So we denote it by psi F. So this is a norm family on F, so it's called a restriction of psi on F. And similarly, if you have a quotient space, so if E to G is a quotient space, so you can consider psi G is a quotient norm. The family of quotient norm. So this is a quotient norm. On G k omega. So this is a quotient space of E k omega. So such norm family is called the quotient of psi on G. So maybe I just mentioned that this is psi dual is called the dual of psi. And this determinant psi, it's called the determinant of psi. Okay. Finally, if for any omega in omega infinity. So the front norm indexed by omega is induced by an inner product. In this case, we say that psi is Hermitian. Okay. So we have set a notion of non-family. So as you have observed last week, the notion of measurability and the integrability are very important in the study of adelic curve. So here we just need such condition. So we cannot deal with all non-families. So otherwise, we cannot define interesting invariants. So for defining interesting invariants, we need to give some restriction. So we say that psi is upper dominated. If for any non-zero section S in E, which is non-zero, so the upper integral. So anyway, for any function which is maybe not measurable, we can always define some upper integral. So if you are familiar with Riemannian integral, so it's somehow which is very common, such a notion of upper integral. But for Lebesgue integral, so or integral over any measurable space, measure space, you also have such a notion. So what you do is just to take the infimum for any function in L1 of omega nu, such that this function is bounded from below by log of s point. And I take the infimum of the integral of the function f omega. So maybe you have already learned measure theory. In measure theory, you have a dominated convergence theorem or something like that. So it is almost the same condition. So you choose some integrable function which dominate from above your function, which is maybe not measurable. So you take the infimum of all such integrals. It will give you the upper integral of this function. So the function is said to be upper dominated if such a thing is finite, it's not infinity. So maybe it is better to say that you can find. So it's the same thing to say that you can find some f in L1 of so such that f is bounded from below by log s point. So if this set is not empty, if the set is empty, then infimum with respect to the empty set is by convention plus infinity. So okay. So we say that psi is measurable if for any s in E which is non-zero, so the function log of non-s point is immeasurable. And then it is not enough to require that psi is measurable and upper dominated. You have some problem of lower dominance. So you also have some other, a little bit of subtle problem. So we need to control at the same time the measurability and the dominance of psi and also the dual of psi. So we say that E psi is an adelic vector bundle if both psi and psi dual are upper dominated and measurable. And that, by definition, so you observe that E, if you take E dual and the psi dual, is also an adelic vector bundle. So this is by definition. So if the dimension of E is 1, so in that case we say that E psi is an adelic line bundle. So in previous talks, when we talked about adelic vector bundle or Hermitian vector bundle, something like that, we always fix some model, integral model, and we require that the arithmetic norms come from some integral model. Here, for general adelic curve, it is not possible to talk about model. So the condition replacing the model condition is this upper dominancy or dominancy condition. So you need this condition to replace the one of similar to some integral models. Okay. So let me give just a small remark. Is that if we assume that the absolute value of Archimedean places are usual, then you have omega infinity is always in A, so it's a measurable set, and the measure of this set is finite. So in fact, we can consider such function. So we consider f, which is defined as log of the absolute value of 2. So f omega is given by this function. Then you find that omega infinity is just a set of omega such that f of omega is greater than maybe 0.1. So, yeah. So in fact, if omega is non-Archimedean, then this absolute value should be less or equal to 1, and the log of this one is less to 0. So if omega is Archimedean, then by the assumption on the left-hand side table, you know that this log is log 2. Log 2 is greater than 0.1. So then this function is integrable. Therefore, the set of omega such that the value of this integral function is greater than 0.1 is necessarily a measurable set with finite measure. Okay. So let me give you some examples of adelic vector bundles. So although we don't have some reasonable integral model, we can always give you something which is similar. So we consider a basis. So we consider a basis of E over K. Then we can define a norm family as follows. So for any lambda 1 until lambda r, which belongs to k omega to the power r, so I need to precise the norm for lambda 1 E1 plus lambda r E-r. So this is given by the max of I, lambda I, omega, if omega is non-Archimedean. And a sum for lambda I, omega is Archimedean. So this is a norm family. So you can observe that the dual norm, so if EI dual is the dual basis. So this is denoted by E dual is the dual basis. So you can compute the dual norm of this one. No, so this is E, omega, and the dual. So this is given by just the maximum of lambda I. For omega non-Archimedean or Archimedean. So in fact, the dual norm of the L1 norm is just given by the subnorm. Okay? Okay, now we claim that E xi is an adelic vector bundle. So I will show only that this dual norm family is measurable and upper dominated. So, for example, if you take alpha, which is B1 E1 dual, plus B R ER dual, which is an element of E dual non-zero. Then, so log of alpha, so E omega star, so it's given by the maximum of I in 1 to R, such that Bi is non-zero. So you always find one I which with bi is non-zero. So you take log of bi omega. So you have the maximum of a finite family of integrable functions. So this is also an integral function. It's measurable and integrable. So once it is integrable, it's automatically upper dominated. So for this function, it's a little bit larger than this one, but using the fact that nu of omega infinity is finite, and this sum is bounded from above by r times the maximum. So you have also the dominancy and measurability. Okay. So I will just state the following proposition. So the following conditions are equivalent. So the first one is if you take psi and psi duo, they are both dominated. So upper dominated. So this condition is equivalent to say that so you can find some basis such that the upper integral of the difference between such norm families, so sup of log s. So here psi is given by omega, omega in omega. So you compare this norm with the norm given by the basis. So then you compute the integral, the upper integral. So this is finite. So you can find some integral function which dominates this difference of norms. And the third condition is that for any basis, you have the same inequality. Any basis of E, this inequality. So this proposition shows that the dominance is good condition to replace the condition that your adelic structure comes from some integral model almost everywhere. So okay, it's not exactly the same, but it's almost the same. So now I can introduce some arithmetic invariants. So we will make a technical assumption. So we assume that K admits a countable subfield. K0, which is dense in K omega for any omega. So why this technical assumption is important The reason is that to keep the measurability of some algebraic constructions, such as quotient or determinant or something like that. So sometimes we need to consider the passage to limit also maybe the infimum of a family of vectors in some finite dimensional vector space. And in general, such procedure cannot preserve measurability. We have some counterexamples. So if you take the infimum with respect to a non-countable family, then even if in the family you have measurable functions, the final result can be not measurable. So such a countability condition will guarantee that usual algebraic constructions will preserve some measurability condition. So for example, a consequence is that so if xi is an adelic vector bundle, then the following are all adelic vector bundles. So for any vector subspace F in E, so if you consider F and the restriction of psi on F, this thing is an adelic vector bundle. So for the dominancy, there is no problem even without this condition. But for measurability, you will have some difficulties. Of course, you can say that, so if you take some element here, you compute the norm, it will automatically be measurable. But you need to not only consider psi f, but also the dual of psi f. The dual of psi f is not an induced, not a restriction, rather a quotient of psi dual. So you still have such problem of taking the infimum or supremum with respect to an infinite family. So of course for quotient vector space, you have also an invariance of adelic structure, so it's an adelic vector bundle. And also for the determinant. So the determinant of E psi, which is defined as the determinant of E, and the determinant of psi. So this is an adelic line bundle. So as you have seen before, once a determinant is well defined, you can construct the Arakelov degree for adelic vector bundles. So just one word about the dominancy. So you need to use this proposition. So for example, if you consider a vector subspace, you can construct a basis which consists of one basis of F and other vectors to complete into a basis of E. And then by using such a criterion, you obtain that the restriction of your adelic structure on F is also upper dominated and also for quotient structure. So you should use the criterion on the proposition on left hand side. Okay. So now I give you the definition of Arakelov degree. So let's X be an adelic vector bundle. So the Arakelov degree of Xi is defined as minus integral over omega log of norm S1 etc. SR omega determinant nu d omega. So here Si is just a basis. Of E over K. So if you change your basis, so you multiply this determinant vector by a scalar, then as we have assumed in the beginning that the adelic curve is proper. So you have a product formula saying that the integral of the log of the absolute value, some non-zero element, is integrable with integral 0. So you don't change the value of the definition. So therefore the Arakelov degree is well defined. Now, so since you are now familiar with the slope invariant, so I will introduce very quickly other invariants. So as I told you, here you cannot define H0 in the usual way by thinking about adelic, the unique disk. That is not the right invariant. So we need to take degree plus instead. So you have already seen in the algebraic geometry of a curve case that degree plus is not far away from the H0. So degree plus of Xi is defined as a supplement of f included in E. So the degree hat of f psi f. So we just consider the degree of all vector subspaces equipped with the restriction of adelic structures. So if E is non-zero, you can define the slope of Xi as the degree of Xi divided by the rank of E. And also you can define the mu max of Xi as the supermum. Here we assume that f is non-zero. So mu hat of f. And also the mu min hat of Xi as the infimum of each quotient space, which is not zero, mu of G psi G. So here you consider the quotient norm family. So you have all these invariants. Just a useful remark is that, so here we don't assume that psi is Hermitian. So there is several differences between this new setting and the classical setting where we consider just a Hermitian structure. So for example, you don't have the symmetry between mu max and the mu min of dual. So a little bit like the minima. So you don't have mu max of E dual. It's the same thing as minus mu min of E. So for example, you can prove that this one is the infimum of all quotient space. You replace mu by mu max, so that is possible. If you replace the mu by mu max, and then you take the infimum, so you have some minimax structure. this is the same thing as the mu mean. So you need some effort, but it is true. For mu max, you don't have, I think, you don't have the similar thing. You cannot replace mu height by mu mean. So, so that there is a true difference between these two approaches. So we will go back to this point a little bit later. So we will find the minimal slope. We will use minimal slope to define Harder sigma filtration in the general setting. Okay. So now, so let me give you some basic notion and the results of slope theory in this general situation. So I recall that so in the classical number theory case, so it's both the theory, or maybe for number fields. But the statement is almost the same, and the idea is very similar. So just line by line generalization. So we consider two adelic vector bundles. So let I bar, which is I, and you have a family of norms, and F bar, which is given by the adelic vector bundles. So we consider a K-linear map. So F from E to F will be a K-linear map. So we define HF, the height of F, as the integral of omega. So log of Fk omega. So this is an operator norm. So here you'll find the operator norm. Of Fk omega. So from E k omega to Fk omega. So you have two normed vector space. You have a linear map between two normed vector spaces. You can consider its operator norm. So under the assumption above, you can show that this family of operator norm defines a measurable function. It is also integrable if f is non-zero. So if f is 0, then you find minus infinity everywhere. So this is just minus infinity. So just a remark. So if E and F has the same rank, then we can compute the determinant of F. Then you have so maybe R. So then the height of the determinant F is smaller than height of F times R. So I can give you a quick proof. So if you have a basis Si, So when you compute f f of so maybe f of e of k omega. So if you compute f k omega of S1, where's etc. where's f k omega Fr for the determinant norm. So by definition, it's the infimum of some complicated, so infimum of different writing of the same determinant vector. So in particular, you have one writing. So by definition, the infimum should be bounded from above by one possible writing. So fk omega of Si f omega. So this one is bounded from above by a norm of fk omega 2 power r with the product of Si omega. And then you can vary, so you can vary the choice of the basis which produce the same determinant vector, and then the infimum of such product will produce you the determinant norm of Si Bldg Sr. So you have such inequality. So the norm of the determinant map is bounded from the norm of the map to power r. So you have such comparison coming from this inequality. So it's not very complicated if you take such point of view. Okay. Then you have the following lemma. So before the statement of the lemma, I give you a convention. So mu min and mu max are defined only for non-zero vector bundles. So for convenience, we introduce some convention that if you take a zero vector space, then you have only one norm family. And the mu max of this one is minus infinity, and the mu min of this one is plus infinity. Okay, then I give you a first lemma. So let E bar and F bar be adelic vector bundles. Of the same rank, and F from E to F will be a K-linear isomorphism. Then you have the following inequality. You have the following equality. So degree of E is just the degree of F plus the height of the determinant of F, and the slope. So if R is not 0, then slope of E is bounded by slope of F plus h of F. So the proof of the lemma consists of noticing that the determinant of F is an isomorphism between one-dimensional vector space. So in that case, the operator norm, so it's just the difference of two norms in some sense on the same one-dimensional vector spaces. So you have this equality, And by using this inequality, replacing height of determinant of f by r times height of f, replacing equality by an inequality, you can divide two sides of the inequality by r, and you obtain the slope is bounded by the slope of f plus hf. So this is not difficult to prove. And then by this lemma, you deduce the following slope inequalities. So we consider two adelic vector bundles. And f from E1 to E2 be a K-linear map. So the first inequality says that if f is injective, then the maximal slope of E1 is bounded by the maximal slope of E2 plus the height of f. So if you have an injective map, you have the comparison between maximal slope. If f is a surjective map, then you have the same comparison but for minimal slope. And finally, if f is non-zero, so you have a comparison of the form mu mean of E1 is bounded by mu max of E2 plus HF. So in the third condition, it's very important to assume that f is non-zero. So for these two inequalities, so you can take f0, and then by the convention above, you will not have a serious problem. And for the third condition, you should take such hypothesis. Otherwise, even with the convention, you will have some trouble. Okay. So I will just explain the first, the proof of the first inequality. In fact, the remaining cases are very similar. So I consider some f1, which is a vector subspace of E1. So with f1 non-zero. Then we take f2, which is the image of f1. Then, since f is injective, so it actually defines an isomorphism between f1 and f2. So now you find the slope of f1 is bounded by the slope of f2, but plus the height of the restriction of f on f1. So this is somehow an integral of logarithmic operator norms. So if you consider a restriction, so the operator norm is smaller, then you find that it's bounded from above by mu max of E2 plus HF. Now, since F1 is arbitrary, so you take the supplement with respect to E1, F1, so you find the inequality. So other inequalities, so just can be proved by a similar way or by some dual arguments. So I will. So maybe dual argument is not good for non-Hermitian case. But a very similar treatment will give you a similar results. So now I will talk about the Hadana-Sima theory. You have already seen this in some abstract setting, but it works mainly for a Hermitian case. So, because there are two things which are important. So, first of all, you need your degree function to be additive with respect to short exact sequences. Second one, you need some convexity inequality taking two subspace in the intersection and the addition. You need some convexity conditions. So all these do not hold in the setting of adelic vector bundles which are non-Hermitian. So you need a Hermitian property to have such nice conditions. So our method consists of treating the theory not by using the mu max. So usually you use mu max to define the semi-stability, etc. So we are rather using mu min. So as I said, you don't have the symmetry between mu max and mu min. So the change is essential. So I will give you directly the definition as an R-filtration. So let E be an adelic vector bundle. On S. So for any T in R, we let F T of E be the intersection of epsilon positive, and then I take the sum of all vector subspaces. So maybe I need E to be non-zero, otherwise it's not so interesting. And the condition is that mu min of F equipped with some restriction of adelic structure. So I require this one is bigger than T minus epsilon. And I take the sum of such F. So it's a little bit complicated. So why I need to take such intersection? So I need the filtration to be left continuous. So it's somehow to force the filtration to be left continuous. So I need the rank function to be left continuous. But a little bit later we will see that in fact we can remove such intersection and just take mu min bigger or equal to T. So this is an R filtration or E. So you have seen in the morning that if you begin with an R filtration, then it will correspond to some 0 equal to E0 included in E1, etc. to some En, which is E, with mu1 greater, etc., greater than mu n. So it will automatically correspond to such data. And then it is possible to prove that this is just the minimal slope of E However, this one is not necessarily the maximal slope. So that is a big difference. Okay. So you need to measure. You need to change a little bit. So you may prove that mu max of E is bounded from below by mu1 and bounded from above by mu1 plus 1/2 log of R times nu of omega infinity. Okay? So now we can rewrite the slope inequality in some more beautiful form. So let E and F be adelic vector bundles. And F be a clear map. For any t in R, you will have f of ft E is included in ft minus hf of f. So okay, I just will not give the proof, but this one we can show that this one is the sum for 0 different than f included in E with mu min of f greater than t, sum of all this f. So clearly this is included in this space, but you can prove that they are the same. So I will give you a proof of this proposition by using such form of definition for this filtration. So we take some m in each, m of 0, such that mu min of m is greater than t. Then you will find that mu min of m is bounded from above by mu min of fm plus the height of f with respect to m. So this is bounded from above by mu min of fm plus the height of f. So that you will find the mu min of fm bounded from below by t minus height of f. So therefore, fm will appear in a sign defining ft minus hf of E. Okay. So in some sense, I give directly the definition for Harder-Nernst filtration. So now the problem is that this definition represents some universal problems. So I will give you some more definition. So we just take degree tilde of E. It's given by the integral minus integral on R. So T d rank, so of Ft E. Yeah. So this is a modified version of Arakelov degree. So you can prove that this is the difference between the tilde version and the hat version is controlled by something similar to such term. So you get involved the rank of the vector bundle and also the measure of the omega infinity. So you can define also a modified slope. So just a small remark. So if for any I, we write mu I hat of E as the supremum of T in R, such that dimension, so the rank of FTE is at least I. So you find that this definition is very similar to what you have observed this morning on successive minima. So you have the filtration by minima, and the successive minima is defined just like this. So then you can do the same thing for a filtration here. And then the modified slope, so degree, modified degree, is just given by the sum of all I, mu I hat of E. So this, it's just something like the sum of successive minima. Okay. So I just mentioned orally. So in the case of Hermitian adelic vector bundle, so if psi is Hermitian, then such definition will not change the value of degree. So degree tilde is the same thing as a degree hat. So you don't need to change the degree. So now I would like to add some more statements in the here. So you can compare. So if f is a clear isomorphism, you can also compare the degree tilde. So degree tilde of E bar is bounded from above by degree tilde of F bar plus the height of F times R. So R is the rank of E and F. So to observe this, you just apply this proposition. So you have a comparison between filtrations, which leads to comparison between mu I. So you have such definition. So then you have mu I of E is bounded by mu I of F plus H of F. So also, if F is injective here, you also have some comparison of mu1. So here mu1 is not necessarily mu-max, so it's useful to make this statement. So So okay. So now we need to justify that such a construction is similar to the classical one. So I need to give you the definition of semi-stability. So if you have a mu1 of E equals to etc. equal to mu R of E, so R is a rank of E. So this means that your R-filtration just have one jump. So you go like E, and suddenly you jump to 0. In this case, we say that E bar is semi-stable. I remind that it's just the same thing to say that for any vector subspace of E, which is non-zero, so the minimal slope, the minimal slope of F is smaller than the minimal slope of E. So you don't have any vector subspace with minimal slope greater than that of E. So if you find something greater, then the filtration cannot jump to 0. So it's jumped to something larger. So it jumped in some place larger than mu mean, not to 0, but to something which is non-zero, so that is not good. Okay, so the theorem says that, so we assume that Ft of E so corresponds to 0 equal to E1 En equal to E. So I write star this flag and the sequence mu1 greater than mu1. Then the conclusion is that first of all, so EI over EI minus 1 with the subquotient family, so it's a semi-stable. And also, you can find the mu tilde of EI over EI minus 1. So this is actually mu min. So this is just given by such mu I. So the first statement is like this, so you have some similarity. The second statement is also similar to the classical setting. So this flag is the only one with semi-stable subquotient and strictly decreasing slopes. So namely, if you have another sequence such that each subquotient is a semi-stable of mu mean decreasing. So the mu mean of each successive quotient is strictly decreasing. Then it should be the same as the star here. So this gives the full analogy with respect to the classical Hadamard-Siemens theorem. So of course we cannot use the initial proof because the most important ingredients are not true. And also we need to modify a little bit the degree function. Okay, so in the remaining time I will give you a sketch of the proof. So, okay, so the step 1 is to show that you have a mu mean of EI is just given by mu I. So first, by definition, you will have a mu mean of EI. So it should be not greater than mu I. So if mu mean of EI is larger than mu I, then you would have find mu I on some so in the filtration someplace after so how to say after mu I, so greater on some place on some t greater than mu I. So that is not possible by definition. So you expect something which is smaller. And okay, for the opposite inequality, so you take some quotient, non-zero quotient vector space. So we need to show that the we need to show that the maximal slope of M will be greater than t. So so by definition of ft, so I use this modified definition. So I need to show that they are the same, but it's not hard. So you can find some f in E with the mu mean of f, it's at least a t, and such that if you construct the composed map, so this composed map is not zero. So because this vector space is just the sum of all such f's. So you can pick some f such that the composed map is not zero. So then you can compute the by the slope inequality. You have t smaller than mu mean of f, and then smaller than mu max of m. So you find that the mu max of M is bounded by T. And then, so you can compute the mu mean of Ft E. So it's just the infimum of such M. So I said that you can replace mu by mu max, so that is important. So this is greater than T. So then this inequality works for ADT. In particular, if you take T equals to mu I, you'll find that the mu mean of this one is greater or equal to mu I. So you have the equality. In particular, you mean hat of EI is greater or equal to mu I. Okay. Okay, step 2 is to show that EI over EI minus 1 is semi-stable of minimal slope equal to mu I. So we just verify that the case for I greater than 2, for I equals to 1, so it comes just from the definition, so it's not so interesting. So because if for the case of I equals to 1, so if it's not the case, it's not semi-stable, you wouldn't be able to add something still to the filtration. So it is not the case. So this is not difficult to see. So we just treat the case I at least 2. So we need to show that any vector subspace, 0 subspace has a minimal slope not more than ui. So we take some G prime, which is included in EI over EI minus 1, which is not 0. Now we consider some projection pi from EI to EI over EI minus 1. And then I take EI prime, which is pi minus 1 of G prime. So this is just the pre-image of G prime in EI. So now, so you have I prime will contain EI minus 1, but it's not equal to EI minus 1 because I assume that G prime is not 0. So, so this will imply that the mu mean of EI prime will be smaller than mu I. So otherwise you can put this vector space on some place in the filtration with index larger than mu I, so that is not reasonable. And for any epsilon positive, you can find some EI prime, some quotient space of H prime, not 0, such that mu of H prime is bounded by mu I plus epsilon. So because of this, so so this if this epsilon is smaller than mu I minus 1 minus mu I, then you will have mu mean of EI minus 1, so which is mu I minus 1, will greater than mu I plus epsilon. So you can observe the composed map. So you compose EI minus 1 into EI. Then EI prime, sorry. Then you take the quotient to H. So this one, the composed map should be 0. So compose the map. So it's 0. Since otherwise you would have a mu mean of this one bounded from above by the mu max of H prime. Yeah, so I should put some mu max here to facilitate the proof, because we can. So as I said, so to compute the mu mean in the infimum, you can replace mu by mu max. So if the composed map is not 0, this one, the mu mean of this one would be bounded from above by mu max of this one. Then you will have some trouble. So what does this mean? So the composed map is 0, namely H prime is actually a quotient of G prime. So hence you obtain a mu mean of G prime is bounded from above by mu I. So thus you will have for any vector subspace, the mu mean of G prime is bounded by the mu mean of this space. So you find that mu1 of this one is bounded by mu I. And the mu I is mu mean of E, so mu I is bounded by mu mean of EI over EI minus 1. So which shows that in fact EI over E minus 1 is semi-stable. So of minimal slope, anyway. So because usually you should have mu1 larger than this one. Okay. So I have no time to develop the uniqueness. So just one word. So you begin with some other flag. So which is not necessarily this one, not necessarily have the same length. So still by using some technique like slope inequality, you can prove that the first term in the flag should be the same thing as E1. And then you pass to the quotient of the vector space E with respect to E1. And then you continue with some induction argument. And then you can prove that you have some equality. So the proof is not that different from the proof that you have seen for the Hermitian case. So I just skip it. So thank you very much.